Hi, my name is Jesse Valdez, and I'm going to help simplify the difficult concept of quantum entanglement. So we begin with the particle. Every fundamental particle can be measured by its spin. It doesn't technically spin, but it has angular momentum and orientation in space, so we can refer to it as spin, whether we choose to measure it in the upward direction or the downward direction. So in order to find the measurement of the particle, we must find the direction of a spin. So the particle can spin upward towards the green detector, or it can spin downward towards the red detector. And so this can only go one of two ways. Either it will go upwards or downwards. So it gives it a 50% chance of doing either or, and this is a probability. So that was if we measured the particle vertically. However, if we decided to measure it horizontally, we would still get these same results. So we would have the green detector and the red detector, and it would still be a 50% chance of the spin going upwards or downwards. There's no difference, and the probability will stay the same. So if you decide to change the angle and direction of which you're measuring, then the probability of the spin going upwards is bound to change. So say you decide to graph it, right? The middle line would be 50% chance that the spin is going upwards. So you start to look at the graph, you'll see it looks like a sine graph. And so let's say we want to use an angle of 60 degrees. That'll give us a 3/4 chance or a 75% chance of the angle to go upwards. And we know this because we're given a formula. And that is that probability is equal to cosine squared half of theta. And this is good because we're able to use this to find the probability of the spin to go upwards at any angle that we want. And so this is a pretty helpful tool to use. So all that information was for one particle. However, it starts to get tricky whenever we use two particles when it comes to measurements. And I'll explain. So if we use two different types of measurements, the first being a square and a circle, and the second being with the colors, say the first particle is red and the other first particle would be green. And so we automatically know that if the first particle is a square, that the second particle has to be a square. And that the same goes for if the first particle is a circle, and it's even the same with the colors. We know that it has to be red if the first particle is red, and that it has to be green if the first particle is green. So let's say we're given a square. So we instantly know that we're given a square, that the second particle has to be a square. However, what we do not know is whether it will be a green square or if it will be a red square. This is unknown. There is nothing that tells us specifically or definitively whether we can determine which color it be. Although there is a 50% chance that it could be either color, and so, but we cannot definitively say that it is one either or. So all this information has brought out great debates whether there's hidden information within the particles or whether not. And what scientists hope to have gained from this was to get instantaneous communication across the universe that is faster than the speed of light. However, for something to be faster than the speed of light, that means it would have to make time go backwards, which would break the laws of relativity. However, this is all false, and because the particles are random and random at that. So even though the first particle would show a spin going upwards, and the second particle would show a spin going downwards, although they are opposite and they will always be opposite, there's nothing continuous about it, and that they are just random and random at that. And so Einstein's laws of relativity do stay true as nothing goes faster than the speed of light. So this is my simplified version of quantum entanglement, and I'm glad to have simplified a difficult concept that stumps many students. And so I hope this sparks an interest for you to learn more about this concept because this could be the future of physics.